Okay, so a guy named Democritus, he gave the very first atomic theory, and he said that all matter is divisible. We can break it apart until they reach this basic unit, which he called an atom. Okay, so we actually still use that word today, don't we? We still use the word atom. But his idea of the atom is a little different than what we know today. Okay, the problem was when he gave this theory, nobody believed what he said. No one believed what he said because there was already kind of a preconceived notion about how the world was made up and what it was composed of. And so he was challenging that a little bit, and people just didn't really understand where he was going with that. So he was not really, they didn't really buy into that. But he did give it the word atom. And so we kind of stick with that today, right? We use that word, but we know a little bit more about it, okay? Aristotle's view on the atom or on matter was that matter was whole and you could not break it into smaller pieces. And so everyone really believed what he said about matter. He had some more in-depth ideas, but he had basically 5 elements, right? Fire, water, earth, all here. Those are the things that Aristotle taught and people believed. But his view or his theory of matter was that it was very holistic. Right, this is a type of earth, right? This is a type of fire, water, things like that. But people followed his ideas for a long time until we started making some different discoveries with that. Okay, so when we get into what we consider the modern era, we're looking at after the 1700s, right? In the 1700s, we really started diving into science and making discoveries and doing a lot of research. And so in the 1700s, people already had an understanding of what an element was. Okay, they had an idea of what an element was. Can we give an example of an element? Shout out some examples of elements. Shout them out. What are they? Sodium. What else? Nitrogen. Calcium. Anything on the table, right? Now we have a periodic table of the elements, but they had a rough idea. They had an idea about chemical reactions. Tell me what does it mean? What has to happen for a chemical reaction to take place? What has to happen for a chemical reaction to take place? Or what's a way that we know a chemical reaction has taken place? Okay, there's a change of substance, right? A chemical reaction means something new has been formed. Right? And we might know that's happened because it changes colors or it changes, it starts to heat up or cool down or there's bubbles or there's whatever, right? Those are a lot of indicators of a chemical reaction. But they had an idea what chemical reactions were. And so they did a lot of experiments and it led to what we call the law of conservation of mass. Okay, that in a chemical reaction, mass is not created or destroyed. Have we heard that term before? Right? Mass is neither created or destroyed during ordinary chemical reactions. It just changes forms. So they understood at this point that if I put in 4 hydrogens to my chemical reaction, I must get 4 hydrogens back out of that chemical reaction. They might be rearranged. They might be bonded with something else. But whatever I put in, I have to get out. That is the law of conservation of mass. And that's what we try to satisfy when we do balancing chemical reactions, right? When we write out chemical equations and chemical reactions, we do what we call balancing. Okay, we balance those reactions to ensure that the law of conservation of mass has been met. That means whatever we put in has to come out. Okay, so they understood what happens in a chemical reaction. They understood a little bit about chemical compounds, and it led to this law right here, the law of definite proportions. That says once we name a compound like H2O or CO2 or once we have a compound established, that compound has the same ratio, has exactly the same proportions by mass, regardless of the sample or the source of the compound. So we know that water always has 2 hydrogen atoms and 1 oxygen atom, right? H2O. Water's compound will be the same. Its formula will be the same regardless of where we get it, how much of the sample we take, all that kind of stuff. The ratio is the same. So it kind of says once we make a chemical compound, then that's it, right? If we change the ratio, now it's a new compound. It's something different. Okay, that seems kind of obvious, don't we think? Right? But as they were starting to put together these rules in science, that was one that they had to write down, basically. Okay. They also understood that we could take 2 elements and put them together in more than one way. We can put them together in more than one way. So this is called the law of multiple proportions, which means we can combine elements in several different ways and get new compounds that behave differently. Okay, compounds are formed by whole atoms chemically combining in different ratios. The example we wrote here is of CO2 and CO. Do you know the names of those formulas? Carbon dioxide and carbon monoxide. They behave differently, right? They have different properties. What about this one? What's this? H2O is water. Do you know what H2O2 is? No. H2O2 is called hydrogen peroxide. Hydrogen peroxide. One of these is fundamental to life. That one is not something we want to ingest, right? Hydrogen peroxide is like what you put on cuts to sterilize things, right? And it bubbles, right? And it bubbles up. You know what I'm saying? Right? It's a totally different substance. Their formulas look really similar, don't they? Their formulas look really similar, but the addition of that oxygen changes the properties of that substance. It does totally different things. And so it's once we have this ratio, right, we change the ratio, we form something totally different. Right? We can put them together a lot of different ways. All right, so let's talk about what we know today about the atom. Okay, today, did I skip over anything, or are your slides following along with me here? They good so far? Okay, good. I want to make sure with this different PowerPoint, it's all good. Today, we know that all matter is composed of atoms. Would we agree with that? Everything is made up of atoms. Do we know what else goes into the atom? What's found inside of an atom? Protons, neutrons, and electrons. That's how I abbreviate those. Protons, neutrons, and electrons. Do you know why I abbreviate them that way? Neutron has a neutral charge, a zero charge. What's the charge of a proton? Positive. And the charge of an electron is negative, right? I'll abbreviate those things in that way. So you might see me write that. P plus, that just means I'm talking about a proton. Okay, so we know that about today. Atoms of one element differ in properties from another element. So they are different than another element. That seems obvious, right? Today's definition of the atom, the smallest particle of an element that retains the chemical properties of that element. I think that might be important for you to highlight that or circle that part, because it's important for us to know that the atom, in order to be an atom, it has to have a certain arrangement of protons, neutrons, and electrons. And to be considered an oxygen atom, it has to have a certain number of protons, neutrons, electrons. And if we start to change that too much, it's no longer an oxygen atom. It no longer behaves like an oxygen atom. And so we know that it can be broken into smaller parts, protons, neutrons, and electrons. But once we break it apart into those things, it's no longer an atom, right? Then it's just an electron or just a neutron or just a proton. An atom has to have all of those things in a certain arrangement that maintains the properties of the element. Okay? All right, so let's talk about the first picture of the atom, what they kind of thought the atom looked like. About the atom, we're going to start with a guy named J.J. Thomson. Okay, his first experiment gave him a model of the atom. Okay, and his experiment said that no matter what type of a metal he experimented with, it always gave off a negative charge. And he called this negative charged particles electrons. So J.J. Thomson really discovered the electron. That was the first subatomic particle that was discovered. So the electron was discovered first. Before the proton, before the neutron, it was the electron. Okay, and it was discovered by a guy named J.J. Thomson. So he said that all these metals are giving off this negative charge. And so through his experiments, he was also able to decide then that means every element has to have electrons. Right? They might mean different things, but he was able to kind of deduce that if all these metals have them, then every element must have these particles, these negatively charged particles called electrons. Later, he showed that electrons have a mass of 9.103 times 10 to the negative 31st kilograms. Is that heavy or light?
Light.
It's very, very light. 10 to the negative 31st. So that means there's 30 zeros in front of that 9, right? Point, 0, 0, 0, 0, right? Point, then 30 zeros, then 9. So it's incredibly small, okay? And in comparison to a proton, it's like 1/1000th of the size of a proton. So it's incredibly small, even in relation to a proton. Knowing what he knew about atoms and about their electrons, this is the atom model that he came up with, okay? This is called the Thomson model, or actually sometimes it's called the plum pudding model. Plum pudding. I don't really know why, okay? Just because I don't even know why. I can't give you an answer. Looks like a big, I don't know. I have no idea. Plum pudding model, okay? But the Thomson model was basically this. It's a little sphere and it's just got electrical charges all over the place. Okay? His theory was that this little sphere had an even distribution of positives and negatives within that atom. That's what he thought, right? He understood that since atoms are neutral, there has to be some positive charges to offset the electrons, and so he called them protons. And he said, since electrons have very little mass, there must be something else to account for the mass of the atom, which he called neutrons. So he was able to give a name to all of these things. And maybe not him only, right? But through his experiment and through his atom, they gave names to protons, electrons, and neutrons. Yeah, that it's just a bunch of negatives spread throughout. Okay, so let's keep walking through this a bit. We're going to walk through next how did we discover the nucleus? How did we know the nucleus was a thing? Now, tell me, where is the nucleus in an atom? It's in the middle, right? It's in the center. But up until this point, they just thought that all atoms were spread out evenly, right? That there was no central point. So a guy named Ernest Rutherford walked through what we call the gold foil experiment. Okay, this is a very, very famous scientific experiment called the gold foil experiment. And he worked with positively charged particles that were heavier than hydrogen called alpha particles. They are positively charged. That's an important part of what we're learning here. It is positively charged. Okay? And so knowing what we know about the model at this point, the plum pudding model said there's just a bunch of pluses and minuses just sprinkled throughout the atom. So when he sent through this alpha particle through the sheets, his expectation was that they were just going to pass right through. They were going to be uninterrupted because he said all the atoms are neutral. These positive charges are just going to run right through it, right? That was the expectation. Here's kind of what he thought would happen. These alpha particles, they might hit an atom, but if they did, they would just run right through it. Or if they didn't hit it, they would still just run right in a straight line. That's kind of what his expectation was, is that his particles he shot through were just going to run right through it. But what actually happened was, so he called that the nucleus. Okay, he said some of the particles are redirected. There must be a small positively charged region at the center of the atom, and he called it the nucleus. So his model of the atom is going to look a little differently because the model that he's coming up with now has a region at the middle that's positively charged and electrons on the outside edge. And so I'll show you that model here in just a second. But he said that electrons kind of orbited the nucleus like planets orbit the sun. They were going to go roam around the outside, and that most of the volume of the atom was empty space. So Rutherford's model is called the planetary model, and it's the most famous in terms of like clip art science, right? If we were going to see a clip art of an atom, this is what we would see, okay? So here is Rutherford's. He ran these alpha particles through this gold foil, and a lot of them did go right through. But some of them were deflected. Okay, they were deflected at the foil and they hit in a different spot.
Did that change it? Did that change the whole?
Right, so that changed the outcome of the experiment. He was expecting them to go right through, but what happened was that they hit something and caused them to change their path. So I want you to think about this. If he was sending in positively charged particles, what would it have had to hit to be deflected? What'd you say? A negative particle? What happens to a positive and a negative? They attract. Positive and negative attract, don't they? It would have to hit another positively charged thing to deflect. Think about when you put like two wrong sides of a magnet together, right? They won't stick, will they? They just bounce off of each other. That's the same thing that's happening here. So he said, if my positively charged particle is being redirected, it must have hit something else positive, okay? Model right here. Okay, this is called the planetary model. Or you might even call it the Rutherford model.
So the nucleus is always positive?
Right. Because what's found in the nucleus is protons and neutrons have no charge. So there's a bunch of protons in here, and there's a bunch of neutrons, but neutrons aren't changing the charge, they're just adding to the mass of the atom. Okay? And so he said that the electrons, one on each of these little orbits, was going to be orbiting around the nucleus. But if we take away this like kind of empty space here, if we take away these lines, we'll see that most of the atom really is just empty space. Right? Because if there's only one electron per orbit, look how much of that is just plain empty space. Right? We see the difference? Okay, so a lot of the atom was able, those alpha particles were able to just shoot right through it. But when one of them did happen to hit the nucleus, then it redirected it, right? So when it hit the nucleus, it redirected. But otherwise, there was just a lot of empty space for that particle to be able to fly right through there.
So it could go anywhere.
Yeah, it could go anywhere through there. Okay, the electrons kind of fall in that orbit, or that's what he said. Today we know actually it's a little bit different, but this was a good basis for us to work on for a long time, right? They went under this model for a long time.
So they don't go through this model?
No, now we find electrons in little pockets, and we'll kind of talk about that in the next chapter, but this was the one that they used for a long time, right? All right, so today we know that the nucleus is made of both protons and neutrons. Protons have a positive charge and a mass of 1 AMU. 1 AMU. Okay, AMU stands for atomic mass unit. And protons have a mass of 1. Neutrons also have a mass of 1. So protons and neutrons have essentially the same mass, right? They contribute to it in the same way. They are held together in the nucleus by what we call nuclear forces. So even though they're positive and neutral, they're able to stay together with what we call nuclear forces. All right, let's go over this one more time. If the proton has a mass of 1 AMU and a neutron has a mass of 1 AMU, we know that electrons, I think, I could be wrong, but I'm pretty sure they have a mass of 0.001 AMU, 1/1000th of a mass. So that's why we don't count them while we count the mass of the atom, because it's so insignificant and so small, it's not affecting the mass of the actual atom itself. Does that kind of make sense? It's so small in comparison. 1/1000th of that is not going to affect the mass of our atom. So we don't count that when we look at the mass. So let's figure out what we do. Okay, we're going to talk about what makes elements different from each other. We're going to learn how do we find protons, neutrons, electrons in our atoms and things like that. Okay, so if I want to know what makes titanium different than chromium, the single identifying characteristic is the number of protons. That's the only thing that makes that's not the only thing, but it's the most important thing that makes elements different from one another is the number of protons. It is also called the atomic number. Atomic number is the number of protons. It will always, always, always be a whole number. We can't have part of a proton. So on our periodic table up here, where is the atomic number located? bottom left. Bottom left. This is the atomic number. Francium's atomic number is 87. It is a whole number. Calcium's atomic number is 20. What's the atomic number for phosphorus over there? P. 15. You should have known that already because you already memorized them. Right? 1 through 20. Yeah, I know. You maybe forgot them, but we're familiar, okay? So the atomic number is the number of protons only. This number never changes. And this is something we need to look at too. This is also the number of electrons in a neutral atom. Okay? What does it mean to be neutral? What's the charge of a neutral atom? What'd you say? What's the charge of a neutral atom? What's the number that represents neutral? 0. So the charge of a neutral atom means we have the same number of protons and electrons. So if I ask you how many protons and electrons are in lithium, what would you tell me? How many protons are in lithium? 3. And if my atom is neutral, how many electrons would be in lithium? 3, right? Neutral means that those numbers match, right? Because they add up to 0. If I have 3 protons and 3 electrons, right? They cancel. That leaves me with a 0. Would we agree with that? Okay, we need to make sure that we understand what that means to have a charge or not have a charge. If my atom did have a charge, it would be listed up in the top, lithium +1. My charge on my atom would be +1 there. We'll talk about charges in a little bit. But if we know if it has a charge or not, because if there's nothing listed up in the top, that means it's neutral. It can have a negative charge also. Yep, we'll talk about what that would look like here in a little bit. All right, so atomic number is listed in the top. On our periodic table here, it's in the bottom. What about your periodic table? Is it listed right on the top? Yes. In the top? Okay, very good. All right. Atoms of any given element always have the same number of protons. So what that means is that oxygen always has how many protons? Tell me how many. Look on your periodic table. How many protons does oxygen always have? 8. Always 8. But it can have different numbers of neutrons. So there can be different versions of oxygen atoms. There could be oxygen that has a mass of 16, oxygen that has a mass of 17, oxygen that has a mass of 18. We can change the mass of our atoms. But does that mean we're changing the number of protons? No. We're changing the number of neutrons. Okay, we're changing the number of neutrons. And when that happens, that is called an isotope. An isotope is the same type of atom, the same element, but different numbers of neutrons. So all of these are isotopes of oxygen. Okay, those are all isotopes of oxygen. When we put this little slash with our number out to the side, that tells us the mass that we're talking about. Okay, it tells us the mass that we're talking about. Okay, Close. We would do zinc, not with its atomic number, but with its atomic mass. So we would say zinc 65. We might have a zinc isotope that has a mass of 67. We might have a zinc isotope that has a mass of 64. Right? There could be different isotopes. That's right. An isotope of zinc. Okay. While we talk about mass here, is that makes up an atom's mass? 16, 17, and 18, they all had 8 protons, because if they don't have 8 protons, they're not oxygen anymore. But we have changed the number of neutrons. This one would have 8 neutrons, this one would have 9 neutrons, and this one would have 10 neutrons. Do we see how that works? Right? The mass is changing just because the number of neutrons is changing. We don't ever change the number of protons because that gives us a new element.
And that's the atomic number.
This is atomic number, right? Atomic mass is protons plus neutrons. So down here, we'd have protons plus neutrons.
So why does it says 8, 9, 10 on the side?
Yeah, because our mass is changing. That means the number of neutrons is changing.
They're all going up by one each, right?
Well, these are just examples. I just picked those numbers. We'll be given numbers that have.
8 plus 8 is 16, 8 plus 9 is 7.
Mm-hmm.
Okay.
Yep. Yep. Do you know what the protons? So here are some examples of hydrogen's isotopes. Hydrogen has 3 main isotopes. The first one is just called hydrogen, right? It's the most common one by far, and it only has 1 proton and 1 electron. Take a look at hydrogen's mass. Hydrogen's mass is just 1.01, isn't it? That means it's by far its most common isotope is just regular hydrogen. Okay, but there's another isotope of hydrogen called deuterium, and it has 1 proton and 1 neutron. The last one's called tritium, and it has 2 neutrons to go along with its 1 proton. So it has a couple different versions, but how do we know what's the most common isotope? Well, we look at the mass given up there. We're going to talk about that in just a little bit, okay? Can you answer, have you thought about this question before? If the atomic mass is just protons plus neutrons, right? Atomic mass is protons plus neutrons, isn't it? Why does this come out to be a decimal?
Because it's a guess.
Kind of. Okay, this number right here is actually an average of the mass of all of the isotopes of this particular atom. Okay, it's an average of the different masses of our isotopes.
So that would be considered high?
This one would what?
Would that consider high then?
Yeah, this one would have, that's right. Okay, so we're going to talk about that in a second. Take a look at calcium's average. It's 40.08, which means by far calcium's most abundant. You know what I mean when I say abundant? Most common. It's got the biggest number. Calcium's favorite isotope has a mass of 40 by a lot because it's so close to 40, isn't it? The average of the isotopes is really close to 40. It's a weighted average, which means the more of them there are, the closer we are. Same with sodium. What do you think sodium's favorite isotope has a mass of?
23.
23, right? Because our average is really close to 23.
Beryllium would be 9.
That's right. Beryllium's most abundant isotope has a mass of 9. What about chlorine over here, for example? Does it have one favorite isotope?
35.
Maybe, but look, it's 35.45. So that's telling me that it has 2 isotopes that are kind of splitting it evenly, right? That means that if I take 100 chlorine atoms, half of them might have a mass of 35, and half of them might have a mass of 36. Right? Do you see kind of what I'm saying there? We're going to talk about how that number is calculated a little bit later. But
Helium would be our set number.
which one?
Helium.
Helium? Yeah, it's 4.0, right?
It is
So
a set
it's
number.
just got 1
It's
isotope.
equally.
Yeah, it's just like all of those atoms have a mass of 4, right? If there's 10,000 atoms, they probably all have a mass of 4, maybe except 1, right? And it's not changing our average.
So what would you say about RB? Was that kind of similar to RB?
Yep. So I would say its most abundant isotope is probably 85, and its next one is maybe 86, right? We don't know exactly.
It's like
Yeah, it's really close. Yeah, good. So the closer we see this decimal to the middle, that means that it's sharing a couple different versions of isotopes, right? But the closer it is to a whole number, we know its most abundant isotope is probably 197. Okay, do you see how that works? Okay, so all atoms have isotope. Just, it depends on, some of them have more than others, right? And some of them have more prevalence than others. Yep. And neutrons. The atomic mass is the number of protons plus the number of neutrons in the nucleus. So when we talk about atomic mass, we're adding up the number of protons and the number of neutrons. So if we go back to our previous examples and we say we were dealing with oxygen. Good. Okay, very good. So let's figure out, how do I know how many protons, neutrons, and electrons are in my atom? How do I know how many protons, neutrons, and electrons? Okay. The atomic number tells us the number of protons and the number of electrons if our atom is neutral. The atomic mass is the number of protons plus the number of neutrons. Okay, so that means if I want to find the number of neutrons, I need to take the atomic mass and subtract what out? Atomic mass minus atomic number, right? Minus the number of protons. Okay, so we did an example here of uranium, which is down here somewhere. Uranium's number 92. And this right here is telling us the mass is 235. Okay, you'll see that we're using isotope 235, even though this says the mass is 238. That's fine. We're using the one that they give us. So we're telling about isotope 235. The atomic number is 92, which means that's the number of protons and the number of electrons. The atomic mass is 235, so we're going to take 235 minus 92, and we get the number of neutrons.
So,
Let's do a practice with that. Let's try gold. AU, and we're going to use the mass 197. Okay, so we're going to use the isotope mass 197. So I want to know the number of protons, neutrons, and electrons in a neutral atom of gold. Okay, neutral atom of gold that has 197 as their mass. So the first thing we need to do is find gold on the periodic table. Did you find it?
79.
Okay, it's number 79, which that tells me what? 79 protons. So there's our number of protons. What does that also tell me? The number of electrons, because we said it's a neutral atom, so our protons and electrons are equal. And then how can I find my neutrons? I take 197, which is protons plus neutrons, and I take out the number of protons. You have your calculator out? 197 minus 79 gives me 118. So that's how many neutrons are present. Okay, we're going to do that in just a minute. Yep, we're going to do those in just a minute. Let's try one more of a neutral one, and then we'll move on to what happens if it's not neutral. All right, we'll do that again. Let's try... let's try krypton. So we're going to do krypton, and we're going to use the mass 84 for krypton. If I don't tell you the mass, if I don't give you that, you're just rounding this one to a whole number. I'll try to pick ones that are really close to a whole number. Okay, so you round it to a number. But I want the number of protons, neutrons, and electrons. Okay, have we located krypton? It's way over here on the right-hand side. Okay, its atomic number is 36, so that tells us the number of protons as well as the number of electrons, because it's neutral, so our protons and our electrons are the same. Right? Isn't it 36 and 36? Is that krypton's number? So now to find the number of neutrons, we take the mass, 84, minus the number of protons, and we get 48 neutrons. So if we're talking about ions that have a charge, atoms that have a charge called ions, if I wanted to change the charge of my atom, would I change the protons? Bless you. That would change the positive part, wouldn't it? But what happens when I change the number of protons? It does change the mass, but more importantly, it changes the... No, it changes the element. When I change protons, if I have 19 protons, I'm potassium. But if I add a proton, now I'm not potassium anymore, I'm calcium. So it changes my identity when I change a proton. So when I want to change the mass of an atom, I don't touch the protons, I change the electrons. Electrons are the things that can be adjusted. Protons don't get adjusted, right? Protons stay the same. But neutrons could change the mass, and electrons could change the charge. That's how we could make that's how we have flexibility with that. Okay? So let's think about, how do I remember anions versus cations? The way I like to remember it for cations, their positive charge is because it has a plus sign right in the name. That's how we remember cations. Okay? Cations has a T, a plus sign right in the middle of the word. That's how we remember that cations are positive. Someone else told.
This bump up one.
Nope. The protons never change. Protons never ever change. So lithium would be 3.
4. Would be left one, right?
Electrons, would they be 4?
Yeah.
They would be 2 because I have a +1 charge.
And it's electrons are negative, so it goes down.
Exactly. A +1 charge tells me I'm short an electron, right? I've got one more proton than electrons, and so my electron number is only 2. And then how do I find the number of neutrons?
3 minus 2.
No, I got to go up here and find its mass. 6.94, we're going to round to 7. So I would take 7 minus the number of protons, which is 3, and I get neutrons equal to 4.
2, 3, 4.
Okay, how do we feel about that? Remember, it's hard to think about because plus, we usually think we're going to add things. But really on a plus charge, we are short of our negatives, right? Our negatives are not there. So let's look at another one. Let's look at oxygen with a -2 charge. Oxygen with a -2 charge. Protons, neutrons, and electrons.
8
Okay, 8 what?
protons.
8 protons always. So for electrons, if it was neutral, we would start with 8.
6. 10.
10. It's 10. Yep, that's okay. We have 2 negatives that are extra, so we've got 10 electrons. Good. How about neutrons?
16 minus 10.
16 minus
10.
8. 16 minus 8 is 8. Right? We take mass minus protons. Mass minus protons. Looking, if my atom was neutral, if there was no charge, I would have 8 electrons. But if I have a -2 charge, that means I've got 2 extra negatives. So I had to take my 8 neutral protons and I'm going to add 2 electrons onto that. So kind of adding them. I just want you to make sure you think about it in terms of the sign. Right? The -2 tells me I had 2 more negatives. Right? And so the negatives have to come in the form of electrons.
And to get the neutrons, you always
I always take its mass, which I get from the periodic table, so 16
by protons.
minus protons. Yep, that's always right.
I know it's on the quiz it always be like that, like Li plus or.
Exactly, right. And if it's neutral, if there's anything listed, it would just be like that with no charge. That would mean my protons and my electrons are the same.
One more,
Yeah.
please.
Yep, let's try this one. Let's go aluminum +3. Aluminum +3.
That's 13.
Protons, neutrons, and electrons.
13
13 what?
protons.
13 protons. So let's skip to electrons. What do we think? If it was neutral, it would be 13,
10.
but we are going to take 3 away. So we have 10, right? Because it says we want to have 3 more protons than electrons. And then neutrons, we're going to take 27 minus 13, and I get 14. Let's try fluorine -1. F, it's just F. Fluorine -1. So protons, neutrons, and electrons. So proton number is 9. Electrons, what do we think? Is it going to be 9?
10.
It's going to be 10. We're going to have an extra negative on there. And then for my mass, I'm going to take 19 minus 9, and I get 10 as well. So there's no relationship on, oh, neutrons and electrons are the same. No, those aren't connected.
Neutral again.
Neutrons would be the mass, which is 19, minus the number of protons.
I mean neutral. I thought you know that.
Oh, if we know it's neutral, there won't be a charge listed. It would just say, let's do one. Let's do bromine, neutral bromine. Okay? Neutral bromine. Let's do protons, neutrons, and electrons. So there's no charge because there's nothing listed right there.
So it's 35.
So protons would be 35, and electrons would also be 35. And what would neutrons be? We'll take 80 minus 35, and we get 45. Okay? Good? All right, last thing we're going to look at today is how do we calculate this number that's on the periodic table called the average atomic mass. This number that's reported on the periodic table is the average atomic mass. We said it's an average of all of the isotopes of that particular element. And so it's actually a weighted average. You know what I mean when I say weighted average? Like if a test is worth 90% of your grade, we have to take it times 0.9 and we put it in the grade, right? It's a weighted average. It takes into account how much of that thing there's present, right? It's not just the average. So it's a weighted average. So to calculate average atomic mass, we take the percent of our isotope times its mass plus the next isotope's percent times mass. We do it as many times as we need to. Okay, so let's go ahead and we're just going to do an example here on the next slide. I'm going to skip over this. Is this printed for you, this equation? Okay, let's go to the next one. We're going to find the average atomic mass of this particular atom right here. There are how many isotopes do we see here? We see 3 isotopes. We see 3 isotopes, and we're going to calculate the average atomic mass using these 3 isotopes. And I'm actually going to change something real quick. I want you to get rid of those decimal points because I made those numbers up. I don't like them. 87% of the isotopes of this particular atom have a mass of 33. Right? That's what it's saying. What?
I don't understand.
Okay, we're going to plug it into a calculator. But this is what it's telling us. The information is saying if we have 100 of these atoms, 87 of them would have a mass of 33. 10 of them would have a mass of 34, and 3 of them would have a mass of 31. That's what we're talking about. It's an average of these weights.
How did they get 90?
These numbers are given to you.
So I can say 90%, 32% is.
Well, these numbers would have to be given to you based on the information about that atom. So we won't ever have to come up with these numbers. They'll always be given to you. All right, so to find the average atomic mass, we're going to take the first percentage, but we have to put it into a decimal. So not 87, we're going to take 0.87. I need to make my pen a little bit smaller. We're going to take 0.87 times the mass. That's going to be added to the next isotope. And we're not going to take 10%. We're going to take 0.10 times 34. And our last one is 3%. So how do I put that into a decimal? 0.03 times 31. Okay, so we're going to do that and add them all together, and we will get an average somewhere between 31 and 34. Okay, we're going to add them up and get an average somewhere between those. So we're going to take 0.87 times 33 plus 0.1 times 34 plus 0.03 times 31. Yep, I get 33.04 AMU, right? AMU is atomic mass unit. Is that somewhere close to what you had?
I thought the answer is 5.
No?
So why did you answer behind the painting of 5?
Well, because I took out these decimal places.
Yeah, that's what
I changed our number a little bit. Yep, I changed our number a little bit. So does this match? What's the favorite isotope? The favorite isotope's 33, right? And so our average is just around 33.
How is the favorite isotope 33? What's the answer?